All right, so in this video, we're going to take a look at applications of the last three skills we have: evaluating polynomials for a given x value, adding polynomials, and subtracting polynomials. And they're all going to happen within the premise of this example. The profits of two different manufacturing plants can be modeled as shown, where x is the number of units produced at each plant. So what they're doing is they're giving us an expression for each plant that represents the amount of profit that that plant would make if it produced X units. So not knowing the number of units that something is producing, it's going to make it very hard to figure out the profit. But it's an expression that if you did figure out, if you were told how many units something was producing, then we could use this thing to figure out what the profit would be. And then for the southern plant, we have a different function, but it also relies on X, the number of units it's produced. So that's the idea there. Let's see what we're asked to do. In our first example, we're asked to find the profit at the eastern plant when the eastern plant produces 100 units. So this is exactly the purpose of having a model. If you know the model and then down the line you figure out how many units are produced, that number of units, becomes something that you can substitute in for X, and all of a sudden this thing is no longer a mystery algebra expression. It becomes a value, a number, a profit. So that would then say this is the polynomial of interest right now, and it represents profit at the eastern plant. And the way we're going to use this thing is now that we know the number of units produced, we're going to make room. We're going to eliminate the X's. We're going to get those out of there, and we're going to instead replace it with what we know it represents in this case, 100 units produced. So there's our structure. I still see three terms. I still see something's about to be squared. It's no longer X. It's waiting for its value. And again, 25 times X has been turned into 25 times, well, we've got a value coming, and the value is 100. So our next thought process ought to be, okay, well, if this is what we're going to evaluate, then order of operations is an important thing to concentrate on. We usually think about reading order of operations from the beginning. Let's look inside the parentheses and see what has to be done. There's nothing to be done there. Next, we'll look across this whole expression and look for exponents. But the more time you spend with the order of operations, the more you realize the last steps in the order are adding and subtracting. So this subtraction sign and this addition sign, in my mind, it kind of breaks this up into three pieces. This term can get simplified, this term can get simplified, and this term, and I know I'm not going to do any addition and subtraction until I've got those terms simplified. So the first term has a exponent on it, and that's going to be the first order business, so our 100 becomes 100 squared, which is 10,000. And then now these two terms each have some multiplication that we can do before we ever add or subtract. So our 300ths times 10,000 is the first order of business, and our 25 times 100 will also simplify. So this takes on the value of negative 300. This takes on the value of 215. Notice the structure is all still good. 1, 2, 3 terms still, because we haven't added and subtracted yet. But now we can do that. So we just learned that if the eastern plant produces 100 units, the resulting profit is going to be 700. We'll assume dollars. In the second example, we're asked to still work with the same scenario, but now we're asked to write a polynomial that gives the total profit if both the eastern and southern plants produce X units. Well, that's a very different problem because they didn't give us a number of units. They still said X units. But they're giving us a way out when they say write a polynomial. They're not putting pressure on us to figure out a number, which is good because they haven't told us what we need to find a number to evaluate. They're saying just leave your answer as a polynomial. Well, this polynomial describes just the profit from the eastern plant if it produces X units. And this polynomial over here represents the profit from the southern plant if it produces X units. So when we're asked to write a polynomial that gives the total profit if both the eastern and southern plants produce X units, I think what I would need to do to find that total is to take the best representation we have of the eastern and add it to the best representation we have for the southern. So our total profit then is going to be the polynomial that represents eastern profit plus the polynomial that represents southern profit. So now we can kind of shift gears to that more abstract thinking. We're just trying to add polynomials, and adding polynomials is about finding like terms, because adding these three terms is just a matter of finding the like terms with it. Although I don't want to add a negative. I don't want to think about it as that. So as I'm getting rid of the parentheses that are kind of just for organization, you're going to notice that I never double sign a number. So adding a negative is like subtracting. Adding a positive is like adding. Adding a negative is like subtracting. So you could think about this as distributing the positive sign, or a positive one even, but I don't know that we necessarily need to do that so much as we have to think when you're adding something, the signs that you see on the number are going to basically remain the same when you get rid of the parentheses. Now it's a matter of finding like terms and organizing them. If you want to write them down, you can. If not, just know in your head that you have to find the 25x has to find the 21x. If they're next to each other on paper and that helps you, then go ahead and write that out like I did. And then we can combine those like terms. So I get my x squared term, my x term, and my constant term. They're unlike terms. They're all necessary parts of the final polynomial. That expression we just wrote is the profit at the two plants combined. All right, so moving on to our third piece of the example, still working with the same scenario. We're going to write a polynomial that tells how much more profit the eastern plant makes than the southern plant if both produce x units. So we're still writing a polynomial, and they're still not telling us what x is, so we're going to have to leave x in our expression. But now we're looking for how much more profit the eastern plant makes. Well, let's not talk so abstractly right now. Let's think about if the eastern plant had made $20,000 in profit, and the southern plant had made $10,000 in profit. To find out how much more this is, we'd have to subtract 20,000 minus 10,000. So I think I'm talking myself into the plan that I'm going to use the eastern expression as my starting point, and I'm going to subtract out the southern expression. That'll help me find the difference between eastern and southern. So there's the expression for the eastern, there's the subtraction, which is part of my plan, and there's the expression for the southern. But now we're into that place where when you're subtracting three terms, you have to make sure you're really subtracting each and every term. We're subtracting a negative term, we're subtracting a positive term. In other words, what we learned was you have to think about distributing that negative sign, or if you're more comfortable, distributing a negative one. So as we go to get rid of these organizational parentheses here, we have to make sure that the negative sign for this from the subtraction attaches itself to this negative, to this positive, to this negative, and we see that happen down here. Negative times a negative is a positive, negative times a positive is a negative, and a negative times a negative is a positive. So now we've got the terms we need to combine. Now I can find the like terms, bring all the signs with it. You'll see, for example, this negative 21x, when it traveled, it's still a negative 21x, and then we can combine our like terms. So our difference, eastern minus southern, is that polynomial there. So it gives you a new tool. If you had to find the difference and someone came along and said, oh, you know what, they each sold 500 units now, you could either plug the 500 here, the 500 here, and then subtract. Sounds like 3 steps to me. Or you could just throw the 500 right in here, and you would find the same result. You would find that correct difference, whether you used 3 steps or 1 step. And that's why mathematicians like polynomials. It might actually be more efficient. So at this point then, we've seen that you can substitute a number and evaluate a polynomial, even in a real world application. You can find reasons to add polynomials, and you can find reasons to subtract polynomials in the real world.